In this video, we're going to be looking at indefinite integrals and the total change theorem. First of all, let's talk about the difference between an indefinite integral and a definite integral. An indefinite integral does not have an upper and lower bound of integration. So we would find the antiderivative and then add our constant of integration. So this would just give us a family of curves. Whereas a definite integral, we know this is finding the area under the curve, so this is just going to give us some number. Here's a table of integrals. Now you should know how to find all of these integrals here for these functions. So take a look at this table, make sure you understand how to find each one of these antiderivatives. An example of finding an indefinite integral. I'm going to, first of all, use some of our properties of integrals to rewrite the integral. We could rewrite this integral using one property as 10x to the fourth dx minus 2 secant squared x dx. And another property, we can bring out that coefficient. Same with this integral. Now the antiderivative of x to the fourth is x to the fifth over 5. And the antiderivative of secant squared is tangent of x, and then plus our constant of integration. So if we clean this up a little bit, we'd have 2x to the fifth minus 2 tangent of x plus our constant of integration. And this is what I was talking about earlier. This would give us some function, but this plus c would translate the graph up or down. So this would give us an infinitely many number of curves, and that's what we call a family of curves. Here's another example of an indefinite integral. Let's rewrite this one. We could rewrite this as the cosine of theta divided by the sine of theta times 1 all over sine of theta. And the reason I did this was to rewrite using some trig identities. This would be cotangent theta, and this would be cosecant theta. And if we checked our table of integrals, we would see that this equals negative cosecant of theta plus our constant of integration. Now this is a definite integral, so we would anticipate getting a value for our answer when we evaluate this. Now I'm going to do this all together. I'm not going to split this one up like we did the last one, so I'm just going to find the antiderivative of x cubed, that would be x to the fourth divided by 4 minus 6x squared divided by 2 evaluated from 0 to 3. So if we just simplify this a little bit. Now, applying the fundamental theorem, we would have f of 3 minus f of 0. So to evaluate this, we would plug in 3, so we'd plug in 3 for all of our x's. Now we're going to plug in 0 for all the x's. So we'd have 3 times 0 squared. Now this quantity here, our f of 0, we can see we have 0 minus 0. So this all goes to 0. So we are left with 81 divided by 4 minus 27. And if we get common denominators, we would have 81 minus, looks like 108, all divided by 4. And that is 27 over 4. So there is our answer, negative 27 over 4. Here's another definite integral. Finding the antiderivative of the first two terms, we would get 2x to the fourth divided by 4 minus 6x squared divided by 2. Now this last integral, I'm going to rewrite it as this, because now we can see the antiderivative of 1 all over x squared plus 1 is tangent inverse of x. And then we would evaluate this from 0 to 2. So if we simplified this before we apply the fundamental theorem, we would have this evaluated from 0 to 2. Now we'll plug in 2, so we'd have 2 to the fourth divided by 2, 3 times 2 squared, plus 3 times the tangent inverse of 2, minus. Now even though we have a 0 at the lower limit of integration, we still need to check it, because sometimes you still can get a value. Now for this particular antiderivative, it doesn't appear that we're going to get a value, but we still should just check to make sure. So this is our f of b minus f of a. So our f of 0, we get 0 minus 0, and the tangent inverse of 0 is also 0. So this all does just go to 0. So we're left with 2 to the fourth divided by 2, which is 8, minus 3 times 4, plus 3 times the tangent inverse of 2. So we would have negative 4 plus 3 times the tangent inverse of 2. You could find what is the tangent inverse of 2, put it into its decimal approximation, but I'm leaving this as the exact value. So that's our answer here. Another example of a definite integral. Let's rewrite this as t squared. I'm going to divide each term by t squared and write it separately. So we would have minus 1 all over t squared. So if we simplified this, we would get 2. Let me put my dt back up here. We would have 2 plus, now these are going to reduce, so we would have the square root of t, which is t to the 1/2, minus, now I'm going to rewrite this one as t to the negative 2 power. Now finding the antiderivative, we'd have 2t plus, now we're adding 1 here, so we would have t to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. And then this one, we're going to add 1 to the exponent to get t to the negative 1 divided by negative 1. So I'm going to put the negative 1 that was in the denominator, combine it with that negative sign, so we'd have 1 all over t. And so we're going to evaluate this from 1 to 9. So applying the fundamental theorem, our f of 9 minus f of 1, we have found our antiderivatives, we're evaluating it at 9, minus the antiderivative evaluated at 1. So we'd have 2 times 9 plus 2/3, 9 to the 3/2, plus 1 divided by 9, minus, now we're plugging in 1. So we'd have 2 times 1 plus 2/3, 1 to the 3/2, plus 1 over 1. We get 18. Now 9 to the 3/2 would be the square root of 9 cubed. It's 27 times 2, 54/3 plus 1/9. Then distribute the negative. We'd get minus 2/3 minus 1. And if you work that all out, it is 32/4. Total change theorem. Now the total change theorem is when we're looking at taking the antiderivative of a rate of change. This will give us the total change. For instance, if we were looking at a velocity function, a velocity function represents a rate of change. We know the velocity is the derivative or the rate of change of the position function. So what would I get if we take the antiderivative of a velocity function? Well, we know we get total distance, which is s of b minus s of a, the total change in our position. That's the idea behind the total change theorem. If we are taking the antiderivative of a rate of change, we get total change. Let's look at some examples of how we could apply the total change. If V of t is the volume of water in a reservoir at time t, then its derivative V prime of t is the rate at which the water flows into the reservoir at time t. So what would the antiderivative from t sub 1 to t sub 2 of V prime of t represent? That's the total change in the amount of water in the reservoir between times t sub 1 and t sub 2. The next one, if C of t is the concentration of the product of a chemical reaction at time t, then the rate of reaction is the derivative. So what would the antiderivative of C prime of t represent? That would represent the total change in the concentration of C from t sub 1 to t sub 2. The next one says if the mass of a rod measured from the left end to a point x is m of x, then the linear density is p of x, which is m prime of x. So if we just wrote it in terms of p of x, which is a rate of change because p of x equals m prime of x, then what would this represent? This is the total mass of the segment of the rod that lies between x equals a and x equals b. If the growth rate of a population is dn dt, then its derivative is the rate of increase in the population during the time period. So what would the integral from t sub 1 to t sub 2 of our dn dt represent? That would represent the total change in the increase of population from the time period t sub 1 to t sub 2. So that gives you an idea of what the total change theorem is about. We're taking the antiderivative of a rate of change, and then here we've looked at 4 examples on how to interpret that total rate of change. Here's a few more that you could look at. The first one would be the increase in cost when production is increased from x sub 1 to x sub 2 units. The next one says if an object moves along a straight line with a position function s of t, then its velocity is s prime of t. So this would represent our displacement from t sub 1 to t sub 2. Now let's talk about the difference between displacement and total distance traveled. If we're trying to find displacement, if we have a graph representing our velocity versus time, and let's say we have this as our graph to represent our velocity, you can see we've changed direction over the interval. Let's say this is t sub 1 and this is t sub 2. We've changed direction over that interval. Now think about displacement. From where I start, if I go out 10 feet and then I switch directions and come back 4 feet, my displacement would be 6 because I ended up 6 feet from where I started. That's my displacement. But if I'm looking for total distance traveled, I would add the 10 feet that I went forward plus the 4 feet that I went in the opposite direction. So my total distance would be 14 feet. Now displacement can be found just by finding this integral, v of t dt, because that will take into account this positive area, the negative area, and this positive, and it will give us the distance we are from our starting point. But if we want to find total distance traveled, we need to find the absolute value of our v of t, because we want this area right here to be added into this area and this area. We want to add in this area, so we would take the absolute value. Well, how do we accomplish that? What we're going to do is look at where did we change direction, or did we change direction on the interval. So let's say this happened at 1.5, and let's say this happened at 1.75. Then we could take the integral from t sub 1 to t sub 1.5 of our v of t. That would give us the first portion, but then we would take t sub 1.5 to t 1.75 and find the absolute value. So we could add this, and then we would add in the last interval, and this would give us our total distance traveled on that interval. Okay, so this one gives us displacement, and this one here gives us total distance traveled. So that's how we can calculate displacement or total distance traveled. Here's an example. A particle moves along a line so that its velocity at time t is, so we have our velocity function, t squared minus t minus 6 meters per second. Find the displacement of the particle on the interval 1 to 4, and then find the total distance traveled during this time period. To find the total displacement, or the displacement, we would take the antiderivative on the interval 1 to 4 of our velocity function. We have t minus 6. So we would get t cubed divided by 3 minus t squared divided by 2 minus 6t on the interval 1 to 4. So if we calculated this using the fundamental theorem, we'd get 4 cubed divided by 3, 4 squared divided by 2 minus 6 times 4 minus, now we'd plug in 1, and if we perform this calculation, we'd get negative 9 meters. That would be our displacement. To find the total distance traveled, we need to determine if the particle changed directions on the interval 1 to 4. So let's determine. We know that if the particle changed direction, it has to equal 0 first, and then it can change directions. So let's see if there's a time between 1 and 4 that the velocity equals 0. So I think we can factor this, t minus 3, t plus 2. So t minus 3 equals 0, so t equals 3. Now this one would give us t equals negative 2. So we can see that we have changed direction on the interval 1 to 4. So we would set up our interval to find total distance traveled. So I'll label this was part A, and let's say this is part B. So we would have to, and let's determine which interval is it traveling left or right. So if we plugged in, let's say 2 to our derivative, we would, and here's our velocity, so that tells us which direction we're going. We'd have 4 minus 2 minus 6. So we're moving left. So that would be a negative value. So we're going to take from 1 to 3, and we will take the absolute value of this quantity, so we would have the absolute value of t squared minus t minus 6 dt, and then plus from 3 to 4, so we would have t squared minus t minus 6 . And when we take the antiderivative, evaluated from 1 to 3, we're going to take the positive value here, and likewise for this quantity, so we would have t cubed divided by 3 minus t squared over 2 minus 6t, and this would be evaluated from 3 to 4. And we would want to make sure that we're taking the absolute value. So when you plug in your values, you'd have your f of b minus f of a. So first of all, you'd plug in your 3 for this one here. So you'd have 3 cubed over 3 minus 3 squared over 2 minus 6 times 3 minus, now we're plugging in 1, so we have the absolute value of this quantity, and then we would have 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus, now we would plug in 3, so we have 3 squared over 2 minus 6 times 3, and take the absolute value. And then if we calculated this, we'd get 61 all over 6, or approximately 10.17 meters. So 10.17 meters, or 61 over 6 meters. And that's our total distance traveled on the interval 1 to 4.